Good morning, everyone. I'm Satoru Takekoshi from the University of Tokyo, and this is Manami Mori from Tokyo Metropolitan University. Today, we'd like to talk about AML injection attack on confidential VMs. Our contributors are Takaaki Fukai from AISD and Takahiro Shinaga from the University of Tokyo. In this talk, we'd like to point out that AML is a serious security risk for confidential VMs that has been overlooked until now. This is the outline of our presentation. First, we will introduce what a confidential VM is. VM stands for virtual machine. Next, we will explain what AML is. AML stands for ACPI Machine Language. Then we will talk about the AML injection attack that we propose. We will explain this attack with case studies from Linux and Windows. After that, we will discuss how to avoid this attack with mitigation strategies. These strategies are aimed at users, vendors, and the community. Finally, we will go over the key takeaway from this presentation. Let's begin by talking about what a confidential VM is. Today, cloud vendors offer virtual machines or VMs to users as a service. For example, Amazon provides EC2, Google provides Compute Engine, and Microsoft provides Azure. In traditional virtual machines, users have to completely trust cloud vendors. This is because once users upload their data to virtual machines, cloud vendors have full access to the data. Even if the data is encrypted before upload, cloud vendor can access the decrypted data in memory during processing. This makes users worry about the safety of their sensitive data. To solve this issue, several cloud vendors have recently introduced a technology called a confidential VM or CVM. A confidential VM uses hardware-based mechanisms to protect sensitive data in virtual machines from cloud vendors. This means that users don't have to trust cloud vendors when handling sensitive data in confidential VMs. This protection is provided through CPU-based encryption and attestation. We will explain each of these techniques in the next slide. First, in confidential VMs, the CPU encrypts the memory data of virtual machines. The encryption keys are stored inside the CPU, so cloud vendors cannot access the keys. The CPU automatically encrypts and decrypts memory data during read and write operations. This allows existing operating systems to run on confidential VMs without any modification. As a result, users can securely handle their sensitive data in confidential VMs without worrying about cloud vendors accessing it. However, even if the memory is encrypted, user data could still be leaked if a backdoor is installed in the confidential VM. To avoid this, users need to perform attestation on confidential VMs. Attestation is a process that verifies the contents of confidential VMs. When a confidential VM boots, the CPU checks memory contents and generates an attestation report. By checking this report, users can confirm that the OS kernel and the firmware running in the confidential VM are legitimate. Here, we are going to review the threat model of confidential VMs. In confidential VMs, cloud vendors are assumed to be untrusted. Instead, we trust CPU vendors to make sure that the encryption and attestation are done for sure. This trust allows users to securely handle their sensitive data in untrusted cloud environment. In this presentation, we will base our discussion on this threat model where cloud vendors are untrusted. Confidential VMs have already been commercialized and are provided by several major cloud vendors. For example, Amazon and Google provide Linux-based confidential VM instances, while Microsoft offers Windows-based confidential VMs. The two major CPU vendors also support confidential VMs, and the CPU with AMD SEB SNP and Intel TDX are widely available. So far, we have talked about confidential VMs. Next, Before going into the detail of our attack method, we will give an overview of AML, the key topic of this presentation. AML stands for ACPI Machine Language, and ACPI stands for Advanced Configuration and Power Interface. ACPI is a standard for configuring and controlling computers. AML is bytecode defined by ACPI and is used to control hardware. It is executed by an interpreter in the OS kernel. The reason why this kind of executable code is necessary is that hardware control like power management needs hardware-specific action in a special sequence. AML code is stored in the data structure called the ACPI table in the firmware. When the system starts up, the OS kernel reads the AML code into memory and executes it. Here, we will show you an example of AML. This screenshot shows AML code related to CPU power management on a specific machine. As shown in the red frame, AML code can perform conditional branching using if statement and access memory through variables. With variables, AML can write to any specified physical memory. In this way, AML has the same expressive power as standard programming languages. An attack using AML was proposed at Black Hat Europa in 2006. It was called the ACPI rootkit. The ACPI rootkit is written in AML and stored in the flash ROM. When it is loaded into memory, it works as a rootkit. But the flash ROM is installed in the physical machine, and software access is protected by a signature. Because of this kind of attack is not easy to do. With confidential VMs, AML is provided by the cloud vendor. This means the cloud vendor can modify the AML at any time. AML is used to configure and control the virtual machine, so it's closely linked to the virtual machine. Because of this, AML can be specific to the cloud vendor. In fact, some cloud vendors use custom AML for their confidential VMs. As I said, the AML for virtual machine is provided by the cloud vendor. With the traditional virtual machines, users trust the cloud vendors and therefore trust the vendor's AML as well. But with confidential VMs, the threat model assumes that users do not trust the cloud vendor. This means users also cannot trust the vendor's firmware. In this case, like ACPI rootkit, the cloud vendor could install a rootkit in the AML. To avoid such attacks, users must always verify AML through CVM attestation. By checking the CVM attestation report, users can find out if the cloud vendor has loaded non-legitimate AML. Now that we've explained the confidential VM and AML, let's move on to our proposal, the AML injection attack. In our attack, we inject AML into the confidential VM without affecting attestation. The key idea is to use the runtime interface to send AML to the virtual machine after it has booted. AML embedded in the firmware is checked during attestation of the confidential VM. However, AML injected after the VM has booted is not included in this attestation. That's right. This injected AML cannot be detected by attestation. This means that the cloud vendor can inject AML into the confidential VM without the user noticing. This runtime interface is designed for communication between the firmware and the host to pass configuration information at runtime. In traditional virtual machines, this interface is useful for improving management flexibility. But in confidential VMs, it becomes a backdoor for injecting AML without detection. This problem comes from a design mismatch caused by the difference in threat models between traditional VMs and confidential VMs. AML injection attack exploits this design mismatch. With AML injection, cloud vendor can inject arbitrary AML code into a user's confidential VM without being detected. This AML code is interpreted by OS kernel, allowing it to perform various actions. So what can cloud vendors actually do with AML code? As we explained earlier, AML code can access the memory inside the confidential VM. However, it was unclear what specific attacks can be carried out using AML injection. In this demonstration, we will show that arbitrary code execution is possible in both Linux and Windows guest through AML injection. This ability for cloud vendors to execute arbitrary code in confidential VM is a serious security issue that contradicts the threat model. Additionally, virtual machines and hosts can communicate easily. This means cloud vendor could easily take full control of confidential VMs by interacting with the code running inside them. Therefore, we can say that an AML injection attack is highly critical. From here, we will introduce case studies for Linux and Windows one by one. Now, Manami will present the Linux case study.
Now, I will talk about a case study of an AML injection attack on Linux. And in this experiment, we use a local computer to simulate the role of a cloud vendor. And first, let's look at AML injection in Linux. In the Linux case, we use QEMU as the host of virtual machine monitor and OVMF as the firmware running inside the confidential VM. QEMU and OVMF are widely used to run Linux guests on virtual machines. And so the OVMF firmware was customized by AMD specifically for the confidential VMs. And QEMU has a runtime interface called the QEMU Firmware Configuration Device, or FWCFG for short. This interface is used to provide various configuration data to the virtual machine. It can also send ACPI information from the host to the OVM firmware at runtime. As a result, cloud vendor can inject arbitrary AML code into the OVM firmware through the FWCFG interface. Next, let's talk about how an AML injection attack is carried out on Linux. The injected AML code is passed from the firmware to the Linux kernel. The Linux kernel then interprets the AML code at startup. We created AML code that rewrites the initial RAM disk of Linux. This RAM disk contains the init script which runs at startup. So, modifying this script, arbitrary script can be executed with a root privilege after the Linux kernel starts. Our AML code changes the init script to open a root shell, and it redirects the standard I/O to virtual serial port TTY-S1. So, through this virtual serial port, cloud vendor can access the root shell in the confidential VM. The root shell is just one example of how easily powerful privilege can be obtained. By modifying kernel memory, arbitrary code can be executed without user noticing. This is part of AML code we injected. It calculates the memory location of the init script and overwrites it character by character. And this code in the red box is writing change root and shell, launcher shell, and redirect to TTY-S1. And this modifies the init script to launch a root shell. This is a video of our demonstration. So we use the QEMU command to run a confidential VM with the option to inject our malicious AML via firmware configuration. So now let's start boot CVM, and this now booting. After booted, we use the SNP guest command to get the attestation report of this CVM from the CPU. So we confirm the hash value of the attestation report and compared it with expected value. This is the attestation report from the CPU. And this is the expected value. Since they are matched, the attestation is successful. But, so as you can see, The cloud vendor can access the root shell in the confidential VM through the virtual serial port TTY-S1. This is backdoor. So we successfully created a backdoor for the CVM. So we can see any file in the confidential VM.
Next, let's move on to the Windows case study. We investigated Windows CVM on Microsoft Azure. Since the source code for Microsoft Azure firmware is not publicly available, we got the firmware binary from an Azure instance and reverse engineered it. Through this analysis, we found that the Azure firmware has two undocumented runtime interfaces that can inject AML code from the host. One uses legacy port I/O, and the other uses data structure in memory. Both interfaces can send ACPI information, including AML code, to the virtual machine. The injected AML code is loaded and executed by the Windows kernel, just like in Linux. But Windows has a security mechanism to protect the kernel from malicious AML. This mechanism was introduced to stop attacks like the ACPI rootkit. It blocks writing to regular memory areas that aren't I/O regions. But we found a way to bypass this security mechanism. We used the memory area called the UEFI runtime service. This area has firmware code called by OS operating systems. This area is rewritable as this is in memory, but it isn't protected by the Windows kernel. By rewriting the UEFI runtime service code with AML, we were able to execute arbitrary code when the Windows kernel is booting. This is the actual AML code we used in the Windows demonstration. In the red box above, we applied a patch to the UEFI runtime service and insert a jump instruction. This jump instruction runs our code, shows in the red box below, inside the Windows kernel. Before showing the attack demonstration, we'd like to give you a few notes. First, this demonstration is a simulation on a Microsoft Azure instance. Since we don't have the access to the Azure host, we use the Windows debugging function to simulate the injection of AML through firmware. We also disabled Secure Boot to use this debugging function. However, this was only required for debugging, and we did not modify any programs in the firmware, bootloader, or Windows kernel. Additionally, we have separately confirmed that on a local machine, it is possible to inject AML through this undocumented interface from a Windows host to Azure firmware. That said, we will omit this part of this demonstration to focus on what can be achieved in an actual Azure environment. Now you see a Windows CVM on Azure through a remote desktop window. And this is the startup folder of the CVM, and it's empty now. Next, we use the debugging feature of Windows to pass our ACPI table. This simulates an AML injection attack. Then we reboot the CVM. Now we have to wait some time before the CVM boot up. Now we have the CVM booted, and yes, batch file run in the CVM. This is done via kernel code execution by our AML. And this is the startup folder of the CVM. Now we have a batch file in it, and this is created from the kernel by our AML. Here we will go over the detail of the Azure environment used in the Windows demo. Specifically, we will explain how we discover the undocumented interfaces and whether they can be exploited. Sorry. For Azure instances, the firmware binary and source code are not publicly available. So we developed a method to dump the firmware from the Azure instance. First, we started a Windows CVM on Azure with the kernel debugger enabled. Next, we used the kernel debugger to pause the CVM. Finally, we scanned the entire CVM memory to locate the magic value expected in the firmware header. Using this procedure, we successfully located and dumped the firmware image of the Azure instance. When we looked at the dumped firmware image, we found two undocumented interfaces that can inject AML. One is called the PCAT bias helper and is part of the ACPI platform module. The other is called the UEFI config blob and is part of the platform PI module. Here is the decompiled code for these interfaces. In the PCIT bias helper interface, it first uses an in instruction to get the size of ACPI table. Then it uses an out instruction to read the ACPI table data. In the UEFI config blob interface, it reads a structure stored at a specific memory address and gets the ACPI table data from it. This undocumented interface can be dangerous backdoors for AML injection because users don't know they exist. That said, is this interface really exploitable? We reported this undocumented interface issue to the vendor, and their response was that Azure host cannot inject arbitrary AML into CVM. They explained that this is because the current Azure architecture includes a component called paravisor. The paravisor exists between the host and the firmware to protect this interface. It is isolated from both the interface and the host by a feature called the Virtual Trust Level or VTL in Hyper-V. If paravisor is working correctly, this undocumented interface may not be exploitable. But can we really trust this paravisor? The paravisor used in Azure is called the Host Compatible Layer, or HCL. The HCL currently used in Azure is proprietary, and its binary and the source code is not publicly available. As a result, users cannot verify the paravisor at all, and must fully trust the vendors for its operation. Additionally, the source code for Azure firmware is also not publicly available, making it impossible to fully verify its legitimacy. As I said, in the confidential VM threat model, cloud vendors are untrusted. However, in Azure, users are required to trust both the firmware and the paravisor provided by the vendor. It violates this threat model, so the current Azure setup does not align with the original intent of confidential VMs. Very recently, Microsoft released a paravisor called OpenHCL as open source. OpenHCL is based on a hypervisor called OpenVMM written in Rust and focuses on providing paravisor functionality. It runs as a user mode program on OpenHCL Linux kernel. Additionally, the firmware we dumped and reverse engineered has been open sourced under the name MSVM. If OpenHCL is used as a paravisor, user will likely be able to attest to the paravisor since its source code is publicly available. However, OpenHCL is not yet being used in the current Azure environment, and its attestability remains a future challenge. From here, we will propose 3 mitigation strategies for the AML injection attack. First, users can mitigate AML injection attacks by performing measured boot with the virtual TPM. AML injected at runtime is not included in the attestation of the confidential VM. Therefore, user needs separately to attest the injected AML. This can be done by including the injected AML in the measurement using a virtual TPM. To do this properly, users need to do 3 things. Use firmware that support TPM-based AML attestation, use a securely protected virtual TPM, and verify the TPM quote generated during the measured boot. Without these steps, users cannot rule out the possibility that the cloud vendor might secretly execute arbitrary code through an AML injection attack. We reported this issue to AMD in May this year. In response, MD notified affected partners and published a public security brief on December 9th. This brief recommends the use of VTPM to include all ACPI tables in measured boot, which matches our suggestion. However, it is important to note that the measured boot feature is still in the previous stage and has not yet been incorporated into the upstream software packages. Secondly, to address issues like the Azure case, cloud vendors should ensure that everything is attestable. Since cloud vendors are considered untrusted, users need to be able to attest to all the code loaded into the confidential VM. To make this possible, cloud vendors must first release the actual binaries loaded into the confidential VMs. Even if users can check the attestation report, they cannot verify it without knowing which binary it corresponds to. Additionally, the source code used to generate that binary should also be made available. Without the source code, third parties cannot verify how the binary works. This includes the binary and source code of the firmware and parameter. We reported the issue of the AML injection attack to Microsoft in July this year. However, as we mentioned earlier, Microsoft says that it is prevented by the provider. When we asked how cloud users could verify that, they responded that the HCL is developed by Microsoft, and as such, CVM users do need to place a level of trust in Microsoft as the cloud operator. They also acknowledged that the current Azure provider binaries and source code are not publicly available. Although they recently released the OpenHCL source code, the provider used in Azure is still HCL and not OpenHCL, and its binary is not available. Therefore, Azure instances remain unverifiable by users. The final mitigation is to improve the security of AML itself. Even if AML can be attested, verifying the security is not simple. Unlike open source software, AML and ACPI tables are used to manage the configuration of the virtual machine. This configuration can vary depending on the virtual machine and the vendor providing it. Additionally, the content of AML can change by modifying the virtual machine's configuration. Because of this, it is difficult for third party to verify the security of AML. Future ways for improving AML security include enhancing the AML interpreter and improving AML verification. For interpreter enhancement, Windows has introduced a basic sandbox as a countermeasure against ACPI rootkit. However, our attack, which exploits the UEFI runtime service, can bypass this sandbox. In the future, more fine-grained and robust sandbox will be necessary. For verification, possible ways include heuristic analysis of HPI tables and AML, as well as comprehensive formal verification. However, these approaches can be implemented in short term, so the long-term effort will be required to study and develop effective countermeasures. Finally, let's go over the key takeaway for each of the three stakeholders in the confidential VMs. For cloud users, we strongly recommend always performing measured boot with VTPM for confidential VM. Without this, you cannot avoid the risk of arbitrary code execution by the cloud vendors. For cloud vendors, we recommend you to make everything used in confidential VMs attestable. This will help build a more trustworthy CVM environment for users. To achieve this, both binaries and reproducible source code for the software loaded into the confidential VM must be provided. For the community, we recommend you to recognize that improving AML security is a long-term challenge that requires sustained effort. That's all from us. Thank you for listening, and we are happy to take any questions. Oh.
Improve Linux with the no ACPI kernel flag. Does it still execute the ACPI tables?
Pardon?
Can you speak a little bit louder?
And if you boot the Linux confidential VM with the no ACPI kernel flag, does it still load and execute the AML and the ACPI tables?
So yes, that's right. So Linux case should booting Linux case on confidential VM without ACPI table is one of the mitigation. But ACPI has a very important data to boot Linux gets and hardware information. So for compatible problems, it is difficult to resolve it. So we must think the alternative solution of ACPI table. So this is not easy way. So I think. Thank you.
Oh, thank you. Did you try any of these attacks on EC2s running the Firecracker VM? In other words, on Amazon's what's it called? I forget basically their new generation hardware that's sort of custom made.
Well, my understanding is that did we solve the EC2 to the my understanding is that you asking about if we examine the EC2.
Well, but specifically the Nitro hardware and the Firecracker VMs, which is now about a third of the whole fleet.
Yeah, we have examined EC2 instances, but not for Firecracker yet.
Okay. Thank you.
Oh. Thank you for listening our presentation, and you don't have any question other than okay. Okay, is it okay? Thank you.
Thank you.